Hello and welcome back for lesson 22. I actually really enjoyed lesson 22 because there's several things in here that I'm currently using in my research that we've been sort of doing in the lab for a while. Hint, hint. So if you happen to be with me, hint, hint, you may see some of this stuff, hint, in the future, hint, hint. Get me? Okay. So the first thing that we're going to talk about is forming an imine. I-M-I-N-E. Imine. And so what this actually looks like is, this is an imine. You've got a C-N double bond in there. And you can react this by adding an aldehyde, and again, an aldehyde or ketone will work, and a primary amine. It's important that you have the primary amine to make the imine. You need to add a trace amount of acid, and this is very pH sensitive. Trust me, it's even more pH sensitive than I thought it would be. So only a few drops of the acid, and the acid in this case is a catalyst, so you just need a little bit, and that's going to form your imine. And here's the mechanism for that. The nitrogen from the primary amine will act as a nucleophile, coming in here to that C-O bond. Electrons go up, and then that negative charge is balanced out by the hydrogen from the acid. The conjugate base from that acid will then come and remove the hydrogen from the primary amine, meaning that we now have something that's nice and neutral. The electrons from the OH go to the hydrogen, electrons go back to the base. You then have a case where your OH, too, is ready to leave. These electrons come up, that leaving group leaves. Note that all of this is in equilibrium, because otherwise it looks like, why would that happen? Well, it happens because it ends up being a little bit more stable and because you have acid to push it. You then take the conjugate base, the hydrogen comes in, or it comes and grabs that hydrogen, electrons go back to the nitrogen, leaving it neutral. Some types of things that are quite often used in making an imine is that we can take a ketone and add what's known as a hydroxylamine. So it's an NH2OH with trace amount of acids, and end up with what's called an oxime. You can also take that with hydrazine and end up making this type of structure, which actually is sometimes both of those are sort of pharmaceutically active. Hydrazine is something that you use sometimes in rocket fuel. So a little bit different applications there between those two things, right? The alternative type of reaction is to make a, oh yeah, it's called an enamine. So imine, enamine. And the difference is that to make an enamine, you end up starting with a secondary amine. And in this case, you end up with a double bond over here for that nitrogen. Now, part of the reason why you end up with a double bond is because note that this nitrogen already has 3 bonds. Nitrogen bonds 3 times. So it has to go up here, because if you had it going to that nitrogen, you'd end up with a salt. You wouldn't end up with an organic compound at that point. Well, you would end up with the salt of an organic compound, but you see what I'm saying. So these work very similarly. The nitrogen comes in to the carbon, electrons flow up. The electrons that we've got here at a negative charge from the oxygen come and grab a hydrogen from the acid, which is, again, pH sensitive. Conjugate base flips out. That then goes and grabs the hydrogen. So note right here, we're pretty much where we were when we were just dealing with the imine formation there. Again, the OH comes and grabs a hydrogen from the acid, conjugate base goes back. The electrons from the nitrogen, again, come up, this guy leaves. And here's what you end up with. An unstable positive charge on a nitrogen that has a double bond. Therefore, the conjugate base that you just made right here will come and pick off a hydrogen that is alpha to that bond right there. So the one that's next door, just like you would have an elimination reaction happen, and that base comes and grabs the hydrogen, electrons go down, this goes out, and bam, there's where you end up with your enamine. A lot of times we take advantage of this and may use reductive animation in synthetic organic reactions, simply because it's much easier to reduce an imine than it is to reduce a C double O bond. So here's what we do often is we use NH3 with trace amount of acids to make your imine, and then you can use NABH3CN or palladium carbon H2 and end up getting your NH2 out here without a problem. It's just more reactive and it's a little bit easier to use that way. Plus you end up with an NH2 instead of a C double O bond, so you can go between the two. Okay, this is a little bit different here, but really sort of the same type of thing. We can make what's known as a Gem dial or a Geminal dial. That starts with the ketone or aldehyde by adding water in the presence of HCl. You can end up with two OHs on the same carbon. If you have a ketone that you're starting with, then the R groups will be there. If you have an aldehyde that you're starting with, you end up with one R group and the other one ends up being a hydrogen. And here's the mechanism. H2O and HCl make H3O+, right? So, as you would imagine, that oxygen comes and grabs that hydrogen, and that makes it a positive charge, which means that water can attack it very easily. Electrons move up. Another water molecule can act as the base and come and grab that hydrogen off there to sort of clean up that reaction, and there you go. We've got two OHs coming off of the same carbon. Now, this gets a little bit more complicated when you deal with alcohols rather than just water and acid, but it's all the same type of reaction here. So if we have a ketone or aldehyde with one equivalent excuse me, of an alcohol and acid, you can end up with what's called a hemiacetal. It sounds like it's really heavy, right? Because it's a hemiacetal, get it? Ba-da-bum. Okay, so that means that we've got one OR. I'm going to put the little line underneath the double bonds here if that helps you see that. Okay, so this R group is coming from here, or is going to there, I should say. And when you add a second equivalent, not only do you have the one down here, but you also have the one up here. And that's what you would refer to as an acetal. Okay, an acetal would be very similar to a Gem dial. And here's the mechanism. These, once again, come and grab the hydrogen, electrons go back, and then instead of a water molecule, your alcohol, oxygens, will come and grab that hydrogen, or sorry, that carbon, electrons go up. Conjugate base, could be the solvent, who knows what, can come and remove that hydrogen, electrons go back to that oxygen. And so after one equivalent of alcohol added, you have a hemiacetal. If, however, this reaction is allowed to continue, then the oxygen from the OH can grab the hydrogen. Now, you may ask, why does that one grab it and not this one? Well, keep in mind, this is equilibrium. If that were to grab it, you just go backwards in the equilibrium here. So, yes, that can totally happen. These electrons can come and grab that hydrogen base, conjugate base leaves. Then, you've got a water molecule ready to leave. So these electrons can come in, that leaves. You end up with this crazy thing down here. We've got a positive charge on the oxygen. He ain't happy. Let's take another alcohol, attack that carbon, because he's ready to be attacked for sure. Electrons go back up, and there we end up with something that looks more like an acetal. Our base can come in, water molecule, I'm sorry, not water molecule, alcohol molecule, it can be anything, comes and removes that hydrogen, electrons go back, and you end up with what's known as an acetal. This is sort of what you would recognize it as more easily. There's two oxygens with R groups coming off of them, off of a single carbon. Okay. So why do we actually care about these things called acetals? Well, we use them a lot because, simply put, this is in equilibrium, right? So you can put these things on and then you can take them off. And we use those as a protection group. And a protection group means that, okay, so in my synthesis, I'm going to make two things that could react with something. But I don't want one to react. So instead of letting it react while I have the other thing react, I first need to protect whatever I need to protect, and then let the other thing react. Here's what I mean by that. If you were to just take this and add lithium aluminum hydride, you'd end up with two OH groups, one in this spot and one in this spot. However, let's say that I wanted to make this. Well, then if I want this ketone or this C-double-O bond to stay in my final product, I need to protect it. I do that by adding ethylene glycol and HCl. So imagine this is your alcohol, but it's just happening to be both ends. And this would be your acetal, where both ends are connected. You can then react it with lithium aluminum hydride, which will turn this guy into an OH. And when you react it with H3O+, that will come off because that's in equilibrium as well, and you end up with that guy. Pretty cool, right? Because you don't want to have to go through and design your entire synthesis based on what can be on there and not react with other stuff. Sometimes that's nearly impossible to do. Sometimes it really isn't very, it's too expensive not to, let's put it that way. Other types of protection groups include this silyl protection group, silyl chloride protection group for alcohols. So you can put this huge guy on right here, and then you take it off with something even bigger, and bam, there's your alcohol. And that means that this alcohol position right here will not react during that time. You can also do like a Fischer esterification for carboxylic acid, so things that you already know exist. Once you add the HCl and an ester or an alcohol of some sort, you create an ester. And then do your other reaction, whatever that may be. And when you're ready to take it off, you just simply go back to the HCl and water. So you remember that's an equilibrium. You just take it off, and there you go. You end up with a carboxylic acid. These are really, really important when it comes to advanced synthesis techniques and very practical when they're in the lab. Okay, thank you very much.